Okay, CTL display capture. I need this one. Okay, there we go. All right, so I'm going to talk a little bit about how to look at Gaussian input files. One of the things that's helpful is to open Notepad. And so we can go in here and type in Notepad, hit enter, and we get this Notepad. And then we go to our any place where we have our Gaussian input files, and you can just drag that input file onto the Notepad. So let's do the optimization and frequency calculation first. So here's our opt and freq calculation. Actually, it's just an optimization you see right here. So Gaussian dates back to the punch card computers, and so we call this the percent card. It tells us the checkpoint file name and the path of our calculation. That's one thing too. If your path is sending it to a network drive, it's going to really slow things down. And so if it's sending it to like a S drive or a T drive here at the university, those are going to be much slower because it's reading and writing everything to a network drive and going through the Ethernet. So that's going to be a lot slower than writing to the hard disk inside the computer. So you really want to use the scratch directory in the Gaussian calculation area because that's on the C drive where it's installed, and it's much faster to read and write from the C drive than to read and write over a network drive. Okay. Then we have the root card, which tells you the type of job we have, which is the optimization calculation, the level of theory, and the basis set. And so I'm doing this calculation for at 6-31G with the d orbitals on the carbons. Then you have to have a blank line, and that sets it apart from the title, and then another blank line, and then you have the molecule specification, starting with the charge and multiplicity. So this molecule is a +1 charge and is a singlet multiplicity, which means all the electrons are paired up. So it's an even electron species once you take that extra electron away. And then this is what's called the ZMatrix. So let me expand this a little bit. Now, I'll explain the Z-matrix. It starts out with the first carbon. I may have to pull up a PowerPoint here. Let me do a blank PowerPoint real quick. So let's look at the Z-matrix. Let me explain that. So if we have a molecule that we want to bond together, how would we specify it? Well, we could use Cartesian coordinates, but that's going to be really a pain for things that are not at 90-degree angles, okay? And we'd rather use bond lengths, not Cartesian coordinates, right? So let's build methane, okay? So we've got methane here. We're just going to start with a carbon here. And so we're going to say carbon. And if, that's all we need to do to specify carbon at the origin. So carbon is going to be at the origin, X, Y, and Z, right? So it puts the first atom at the origin. And so all we need to do to specify the location of carbon is just put the atom there. And Gaussian puts it at the origin. But then what's the next atom? We're going to make methane, so we have hydrogen. So that's atom number 2. And how do we specify where the atom is?
Attached to carbon.
It's attached to carbon. And so we say it's attached. So I'm going to label these carbon 1, H2. So I'm going to label the atoms also with their number. And so we have carbon 1 and H2, and it's connected to atom 1, okay? And what distance? So this is the attachment. And then this is the distance. So R, C, H. So that's the bond length of carbon hydrogen is the next number. So and it by default, I think it puts it on the x-axis. So I'm not sure. So we'll just put it here just for grins. So we have that hydrogen here, and that bond length here is R, CH. And so now both the locations of those atoms are listed. That's fine. We just have it relative to the origin, and Gaussian automatically puts it on one of those axes. And so we have specified this molecule in all its 3 dimensions. The Cartesian coordinates for carbon are 0, 0, 0. and the Cartesian coordinates for H are RCH in the X direction, 0 in the Y direction, 0 in the Z direction. So we have all 3 degrees of freedom specified for both of our atoms. There's 2 atoms, so how many degrees of freedom should we have? 3 times 2? 6. That's the number of Cartesian coordinates you have. 3 for the first carbon, 3 for the hydrogen. So, all right, so now let's do H3. Okay, what's it bonded to?
Carbon 1.
Carbon 1. What's the distance to carbon 1?
R.
CH, yeah. So that's the benefit of the Z matrix. It's the same distance from the carbon. We can use that number over and over again. We can even use a variable. And so we can define our variables down below. And it can optimize that bond length independently of all the other things. But now, where's it going to put that hydrogen?
It's going to be relative to 109.5 degrees.
Yeah, so we'll guess on that. So we'll say now, so now we need an angle, right? Angle, I'll call it angle reference. So it's an angle, how do we define the angle? So it's attached to carbon 1, and how would we define an angle now?
Relative to another hydrogen.
It's got to be relative to H2. So you see I have H3 attached to carbon 1 at a distance, angle from H2 with the angle, okay? So this would be angle HCH. And that's going to be a variable. Okay, so that'll be the degrees, HCH angle. So this is the Z matrix, is what we're making. Okay. So somewhere over here, let's say it's in the XY plane, we have an H. Okay, and so this is the angle here. So this is RCH, and this is AHCH.
So,
and so we've now specified all 3 degrees of freedom for this atom too.
So when it was just punch cards, you had to write in all this?
Yeah. Every one of these would be a card. Like H2, the next card would be C1, the next card would be RCH, would be a number. You punch in a number, decimal, and it's power of 10, you know, if you had double precision, and then you punch in H2, and then you punch in, yeah. Yeah. So God bless us for computers. You know? So then H4. But see, notice how the Z matrix is so easy because it's so intuitive, right? H4 is connected to C1 as well. So we would just put a C1 here. And what's the distance? RCH. Okay. And then now we need an angle with respect to, you know, whichever one. So which one should we choose? Let me go ahead and put a 1 here and a 2 there.
You don't do both.
I'm sorry, 2 and 3. 2 here and 3 there. All right, so now where are we going to put H4?
Shouldn't it be from both hydrogens?
Yeah, so how do we do this? Let's go ahead and define it from H2 again. Okay, so we'll say H2 and AHCH. That's the same number, 109.5. But we now have either a collision with H3 or it's somewhere on this cone back here. You see, it's the same angle from H2, but where is it along that cone?
Right.
Do you understand? Or that ring, right? We've defined an angle from H2, but we haven't defined where it is around that ring. So we need to define it relative to H3. Do you see what I'm looking at now? Mm-hmm. And that's a dihedral angle. Dihedral reference. And so we're going to say H3 is our dihedral reference. And so we have H2 going back to carbon, going back to H3. And so we want it to be a third of the way around. 120 degree dihedral, because it's the angle, it's this plane here, and this plane here. So it's the angle between those planes.
So it's still forming that pyramidal shape.
Yes. So it's H3, and this is the dihedral angle. And we'll call those D. And this is H, C, H, H. So it's in that order: H2, carbon, H3, H4. So it's that H2, 3, 4 dihedral. So you define the first H2, carbon, H3, and then the dihedral to H4. So that's why there's 4 centers here, and that's going to be the angle 120. This one was 109.5, right? And this was, 1.1 angstroms, roughly. So now we have, once we have dihedrals, notice with every new atom now, we've got, let's go ahead and do H5. Bonded to C1 at a bond distance is RCH. Angle with H2 at angle HCH. And then dihedral with H3, and all we got to do is change the sign on that one. D, goodness, why did I write C? So minus D, H, C, H, H. Okay, so we've gone the other way and put that hydrogen back here. And now that molecule is symmetric, and we change those dihedrals, it'll move those hydrogens together. We can optimize this whole molecule with 3 variables: a bond length, an angle, and a dihedral. And we can define it with those 3 numbers: 1.1, 109.5, and 120, and get really close to the tetrahedral description of a molecule. Isn't that easy? And we did not have to do any sines and cosines. None of that. That's why the Z-matrix is so powerful. And now every new atom, let's say we go beyond this, notice now every new atom has a bond length, an angle, and a dihedral, which is our 3 parameters.
Right.
So every molecule has 3 degrees of freedom. The only reason the first 3 don't is because Gaussian makes some assumptions. The first one's at the origin, so it's 0, 0, 0. The second one is along an axis, so it's something 0, 0. And then the third one is just one angle away from that, and it's in a certain plane. And so Z is going to be 0. So that you have 3 zeros, 2 zeros, 1 0, and then from there on, no zeros.
Right.
Yeah. And so that's the Z matrix. And so you're seeing that in this file in Notepad. So these are the carbons. And this is bonded, atom number 2 is bonded to atom number 1 with this bond distance. And atom number 3 is bonded to atom number 2 with this bond distance. And angle with number 1 with this angle.
So they're all integers?
No, down here they're defined. And so down here you can define all of those variables. And these are all the bond lengths, angles, and dihedrals in this amine molecule. And there's a lot of planar rings, and so you see lots of 180s. Okay. Yeah, very cool. And the cool thing about this too is if you know how to make the Z matrix, okay, then you can come down here and you can scan one of these variables. So if you want to map out the potential of a dihedral angle, then you find that dihedral angle and then you scan it. So you scan as a keyword in Gaussian, and you say scan this angle with this many steps at this many degrees. And so you can skip along at 10-degree steps, and you can map out the potential of like a steric hindrance or something like that. If you want to see how much of an energetic bump it takes to spin a methyl group or something, you can scan that dihedral and look at the energy barrier that it goes over. But really, to scan those things, you have to understand the Z matrix. And it really makes things much, much more friendly if you understand the Z matrix. Now, there's a Z matrix editor in Gauss View. So if we pull that up, let's see, do I have anything open? Let me try to find one. Well, let's just try one of these amines. Okay. This is going to be a really ugly Z matrix. Okay, let me try to find one here. So we have this dihedral angle button here. It says modified dihedral. And let me turn on my labels. So view labels. And so now I can see all my labels. Yeah, good. So we have like a 12, 1, 2, 3. So this dihedral angle here, 12, 1, 2, 3. You see that's a dihedral between two planes. It's the angle between the 12, 1, 2 plane and the 1, 2, 3 plane. Do you understand what I'm talking about with dihedrals? Let's make sure we're clear on that. Okay, so resume slideshow. Let's go back to our friendly molecule, hydrogen peroxide. Okay, remember that one? Okay, so we had we had it as this HOOH. Okay, as a planar molecule, it was a C2H molecule. But what if it was twisted slightly? So let's look at the end here. So we'll look down the end here, and we'll do a Newman projection. So we have the hydrogen in the back. And y'all did Newman projections in Dr. Gross's class?
Yes.
Okay. And so that angle is 180. That's the dihedral angle, 180. It could be something else, right? It could be something like 120 if we wanted to. I don't know why it would be, but it could be, right? So that's the dihedral angle. Let me draw another line there. And so how do we define that dihedral angle? Well, look at this molecule up here. We have 3 centers right here. That triangle is a planar object, right? A triangle is a plane.
3 points.
Yeah, 3 points that are not collinear are define a plane, and this triangle is a plane. And so what a dihedral angle is the angle between the planes. Does everybody follow that? Like my hands are planes joined by these thumbs, and it's the angle between the planes.
Now, those 2 planes don't have to share any point. They
share a line. They have to share a line.
Yeah.
Because the line defines the angle.
Okay. I was figuring like if they were like here, this one still has an angle, this one still has an angle.
The only planes that won't share, I'm making a geometric claim here. I'm trying to make sure if it's, but the only planes that don't share a line would be parallel planes. So if they are not parallel, they're going to intersect, and they're going to intersect and form a line. And there will be a dihedral angle between those planes. Yeah, so they have to have an intersection, and the angle has to be you know how you draw the angle? It has to be that angle has to be 90 degrees. Like the angle is, yeah, it's got to be, 2 vectors perpendicular to those surfaces, right? So that angle can't be sort of, I don't even know how you would conceive of an angle that's off axis, but the point is, when we look right down that line here, we're looking down that intersecting axis. That's what we're looking at with the Newman projection. And so the Newman projection, this is the side of one triangle, and that's the side of the other triangle, and that's the angle, the perpendicular angle of those 2 triangles. Does everybody understand what a dihedral is? This is a really important concept in molecular structure, is what a dihedral angle is. And so that's what we're defining here with these things. So we have to have 4 centers to define the dihedral angle. We have the atom that we're talking about, H5, and it's bonded to C1. It's got an angle with H2 and a dihedral reference with H3. So these 2 right here form the axis. These 2 right here are in both planes. Let's see, is that right? H2, H2. H5. H2 angle, H3 angle. I'm just making sure that it's I think it's the first two. Looking at the picture that I drew, it's the first two that define the axis. Okay. Okay. No. In this particular case, the first two are the ones that define the axis. You see, this is the plane here, this H2C Cl, and then the other one is the H2 CH3. So that's the other angle. So let me draw this a different way. So H2 is on top. The carbon 1 is there. Carbon 3 is here. And we've defined carbon 5, or carbon, I keep saying carbon, it's hydrogen 5 here. So we said that hydrogen 5 is bonded to C1, okay, and it's an angle with H2, and then it's a dihedral angle with H3. So when we say dihedral angle with H3, how is it related to H3? It's this plane, H2, C1, H3, and this plane, H2, C1, H5. Mm-hmm. And so it's that angle between those planes is 120. This is 109.5, and then we have the bond length. So the axis of this dihedral is the C1, H2. Does everybody understand that? Okay. Now for this one, we would have we'll call this H1, O2, O3, H4. And so for the H4 line, we had an H4 bonded to O3 with a bond length, okay, bond length of OH, and then an angle with O2. Does everybody follow me so far? An angle with O2. We're looking at H4 here, so angle with O2 of angle OOH, and then the dihedral with H1. Dihedral, and that dihedral would be H1, O2, O3, H4. So that's the HOOH dihedral. And then we would define that as 180 or 120, whatever that dihedral is.
So like the last three atoms in the dihedral angle kind of defines that plane that you're looking at.
Yes. And so the yeah. And so then the last ones here would be the O2, O3, H1. So that's again, those last three are defining this plane. Yeah. And then the H4 is bonded to O3. And so that's going to be, again, this is going to be defining this other one. H4, 3, 2 would be the other plane. Yeah. And so knowing how to make these dihedrals in Gaussian is really helpful. So if we get to this molecule, and we've got our dihedral scanner here, and we've got Gauss view, we can change this. It's reading 30 degrees. We could change it with that dihedral editor. Okay. We can cancel that. We can come up here and look at the ZMatrix Editor. I think it's atom list. And so here we have our Z-matrix, and now you know how to read these things. We have the atoms here, and then the next atom, and the next atom, and the next atom, and then we have the bond length, the angle, and the dihedral, and it throws in the Cartesian coordinates. So we have all of these things that we can use, and we can come in here and we can edit these things. Like this one's really close to to 120. So I could type in 120 and hit enter.
I was going to ask if XYZ updates, if you update that.
Did it? I didn't notice.
Yeah, I did.
Okay, so let me do this one at 120, right? 120, and I'll hit enter. Yeah, and they changed.
Okay.
And so we can come in here and we can lock down the structure exactly the way we want it. Like if we want it defined as 120-degree angles, we can put in exactly 120 degrees. And we can come in and set our 179.9s to 180, and we can really lock in the symmetry. Now, if we symmetrize the molecule, it may do that. Okay, this is a kind of a big and unruly molecule. I know it doesn't have a lot of symmetry. Let's see, symmetrize, yeah. Okay, it says it's a C3 molecule. Now let's go back and look at that atom list. Nah, it's to within, small uncertainties, 0.01 degree or whatever, but you could make it exactly, 180s and 120s and those kinds of things. And then you could identify which dihedral angle you actually want to expose so that you could scan it. So you can reorient these things. So let's say we wanted, instead of that atom 12, we wanted that to be, say atom number 3 or something. I think you can change these. Maybe it's this one. Yes. Okay, so now this is atom 3. And if we go back to that molecule, then we can define our dihedral as 1, 2, 3, 4, and then we can scan that one. And so you can rearrange the order of the atoms from what Gaussian picked first. And then you can specify, this is the dihedral that I want to scan. This may not be applicable to your research, but it may. If it pops up, then you need to know how to do this. And this is super advanced compared to what I had to do when I started out. We didn't have any of the visualization, and we certainly didn't have this ZMatrix editor. And so I was in Excel, typing in the numbers and trying to build my molecule with the ZMatrix that way. And so it's just, I'm glad you guys have these tools. You can do bigger molecules. I could do 10 or 12 atoms pretty easily with the ZMatrix editor, that I built in Excel myself. But now you can pull in a huge molecule and redefine which atoms you want to talk about and let everything else do what it's supposed to do. And you can scan angles and stretch bond lengths and do transition states and all of those things that would be really just nearly impossible to do in the past. So you have a huge tool at your disposal.